Okay, well, thank you, Ben. First, good morning, for those in the Americas, and good afternoon for those in Europe / Africa, and I guess good evening for those in Asia and Oceania. Thank you, Ben, for the invitation to be here with you guys. It's great to be here. It's a great pleasure to be talking at Cornell about estimating density from PAM data, especially it being a place with such a long-standing tradition in bioacoustics. And I guess as the title certainly implies, and as Ben said it, this talk has my project Accurate as the background. I must admit, I'm not as focused as I should be because I managed to overbook myself and I'm actually delivering a class at the same time, but the students are doing their own thing. So I should be good to go. Oops, what's this? I had something on my screen. I guess, given Ben said what he did over his email, this talk is going to be a big disappointment, and I will point the finger at Ben for the raised expectations, okay? The movie trailer description is sent around probably has some of you far more excited than one would hope for, and I guess honoring that call, I've tried to add some movie-themed connections through the talk. So I would like to say a big thanks to you and to listening and to the Accurate funders, which is the US Navy LMR research program, but also to all those that actually give me the tags or give us, because Accurate is a very big thing, the tags that we use to do the project. If you want them, the slides are available at the link on the QR code there. It's still, if you do the download now, it would be a preliminary version because I finished doing the slides 2 minutes before the talk. So wait to the end of it to actually grab the proper version of the slides. You will note that I have the show your color stripes a bit all over, which is a visualization developed by Ed Hawkins to convey the urgency of climate changing and what we can do to prevent a catastrophe on a global scale. And so that will sometimes show in the background. They say that a good image is worth 1,000 words. That's the same with the paradox of climate change. And sometimes a good image forces us to see the unexpected. And I think that, the day after tomorrow might be grimmer than we'd hoped for. And while I might be preaching to the converted here, I guess, I am also convinced that talking about it all the time might help to raise awareness, so I do it. I leave here also a link to a very interesting paper about discourses of climate delay, because I think acknowledging them to fight them is fundamental. Okay, anyway, preaching done. Today I wanted to tell you a bit more about who I am. Ben said that this was part of it, so I put a bit of context. Since most of you will have no idea who I am, then focus on passive acoustic density estimation, and with having background accurate, and hopefully I'll be able to tell you something that you didn't know before and put a smile on everyone's faces while doing it. Now, the plan for today is that, who am I? Then a little bit about how do we observe nature, a little bit about doing it through passive acoustics and animal density estimation, a Q counting example, some accurate sprinkles, and some take-home messages. I might go a little bit all over with the order, but you'll see that that's the overall plan. In fact, I have been living on the edge between statistics and ecology for a long time. That's where I've worked. I've started, as Ben said, my undergraduate studies in biology back in Lisbon. Then I did an MSc in statistics already, trying to understand why and now should we collect the data to find the answers to the ecological questions that we might have. And then I went to St. Andrews to do a PhD in statistics. And so I live in the middle of these crossroads and sort of I'm a mess in terms of who am I, but I'm just very many little different things that make a whole. If I do a cloud, a cloud map of my paper titles, that's what you get. And so clearly you can see that it's about density, it's about sampling, usually distance sampling, typically whales, but also many other animals. And so That's the context of my research today. I sort of here switch gears from kind of who I am to how we observe reality. And we observe reality through filters, right? We do some sampling of the environment, and then our objective is to, based on the samples that we have, make some inferences about reality. But uh, unfortunately, those filters are often difficult to understand. But if we don't understand those filters, we might actually not be able to undo the process that is needed to observe reality. And so typically we'll rely on models, okay? All sorts of models, and most models are wrong, okay? Most models are crude approximations of reality, like the picture on the right, but they can be very useful. And so we will leverage on models which are useful. Here's just an example of how one might observe nature. Occupancy surveys. They could be acoustic occupancy surveys, where you put some sensors on a field, on a forest, and different sites, and then you observe where you've seen or not an animal at each one of those sensors, say on each one of different days. And you can have different types of observations. You might have places where the animal wasn't present and you never see it, and places where the animal was present and sometimes you saw it. But you might also have what we call false negatives. The animal could be there, but you never saw it on any given day. And further, sometimes you could have a false positive, which is the animal was never there to begin, but you do see it. And so, in general, methods to account for animal density estimation or to allow animal density estimation need to consider all these different choices. Now, all these different choices also relate to this notion of the filters and the notion of uh, what we call survivorship bias. That image on the left is a famous image where in the Second World War, engineers were looking at the places where planes would have holes in them, and they were thinking that they should be put armored plates in these areas that were heavily targeted. Until one engineer in particular said, wait a minute, the planes that return is what we are seeing. The planes that were missed, the planes that we are missing, are the ones that got shots in places that put them down. So that's where you want to put the armors. And in fact, that sort of switched completely the approach to the problem. And here is the same. The data that we see from nature has always been through some filters, through some availability bias, to some survivorship bias, etc. We need to consider it. Because, in fact, and I come from, most of my data comes usually from cetaceans, it's really difficult to see the natural world when the natural world does not want to be seen. This is an example from a depth profile from a Blainville beaked whale in the Bahamas. And as you can see, that animal spent 3 nights, that's the shaded areas, and 4 days, that's the light areas, going to depths of 1,000 meters, spending almost 90% of the time below 3 meters, which means that if you're on a boat, you really can't see it. And so to study these kinds of animals, naturally, passive acoustics becomes a very tempting option, because most of these animals do produce sounds while they are at depth, and therefore trying to use their sounds to count how many there are is a very tempting approach. Now, with this audience, I guess I don't need to show you what a spectrogram is, but in general, I like to show this so that people that are not used to sound realize that sound can be translated into patterns. Those patterns can be represented visually, and therefore we can use all sorts of tools to find the sounds in the recordings, and say using machine learning tools, deep learning tools, to find the sounds of interest in long-term recordings, which nowadays we start to have. So it's no longer possible to look at all the data that we collect. We have to have some sort of automated methods to deal with it. Anyway, as I said, you don't need that video in this audience. Now, the context here about population abundance, we need to estimate it. It's very useful for management, and getting accurate estimates is fundamental. Traditional visual methods have a number of shortcomings, especially, as I said, for cetaceans with deep behavior, elusive behavior, long periods submerged, depending on good weather to site them, hard to monitor over time in distant areas from land. PAM might become a very nice approach and is being increasingly used to monitor, but also in particular to do density estimation. Now, there's many options. Once you start trying to estimate abundance from passive acoustics, there's many options. That flow chart comes from a paper from 2013, so it's 10 years old now, but still the different options available are kind of laid there, and there's different things that you need to consider. I'm just highlighting with the image on the right on the website of the project, which I'll share later. There's actually some videos, some science outreach videos that deal with each one of these components that are relevant and that I will talk about here. Now, if you think about one of the ways of estimating abundance, which is Q counting, which is what I'll focus here, a Q counting density estimate is that formula on the top left, and it involves a number of things. But it involves the number of sounds that you've detected. It involves the false positive rate, which is performance of your classifier. It involves the probability of detection, and it involves the Q rate. Now I'm highlighting here the Q rate because that's what the basis of the Accurate project, as you'll see. But if that formula over there looks confusing, if you think about it and if you simplify the units of each one of its components, you end up with animals per area, which is density. So that makes sense. And we will need all these multipliers to be appropriate for the time and place where we've done our survey. Otherwise, there might be bias. So what I'm going to do now is to look at each one of these different components and talk a little bit about how we might go about finding them. So regarding the number of sounds, right, and the number of sensors and the time we sample, that's just a matter of logistics and money, right? Here, this example is taken from the largest, at least that I know of, dedicated survey from passive acoustics at sea, which was 300 sensors. These were sea pods put in the Baltic to estimate abundance of arbor porpoise. Well, that's amazing because you have just what you want. You have a regular grid covering the entirety of the area that you're interested in, and you have detections on each one of the sensors on that grid. So it's very easy to make estimates of density over this area, provided that you have all the other parameters that are required. Unfortunately, real life is not like we want, and as I already shown. And so instead of 300s, the first time I remember doing this, there were 3. So that's just a little bit less, but you could pull it off because it was a proof of concept. And so we were estimating right whales, North Pacific right whales, and we only had 3 sensors. Now, the only reason we managed to publish that was because it was proof of concept. Nowadays, with 3 sensors, you're really pushing the limits. You can't really do density estimation because of a number of aspects, but I'll talk about a little bit more about that if you guys want at the end. Now, the other component that we need to deal with is the probability of detection. We need to find a way of estimating how far away from our sensors we can actually detect the sounds. That screenshot is taken from the same paper with the 3 sensors. So one of the reasons we managed to do it was because it was a very special area where we could use the sound propagation and the degradation of some features of the sound with distance to estimate the actual distances at which the sounds were being produced. And in that way, use what we, traditional distance sampling, very common in terrestrial environments with visual observers, where we model the detectability as a function of the distance from the transect line, and we estimate abundance from that information. Now, unfortunately, quite often at sensors, in particular single sensors, if you have arrays that might be different, but with single sensors, we really don't know what the distance was that these sounds were produced. So we need to do something which might be second best. So as an example of second best, here's a survey of some birds in Hawaii, the Yamaki, and what we've done there was conducting some trials with some animals at known distances and seeing what was the sound pressure level received for those animals at those distances, and then creating a model, a GLM, where we would predict the distance as a function of received level and then use that to do distance sampling. So that might work. Another option that might work is having trials with animals at known distances. So there's no need for calibration, but you need to set up those trials. It comes, the example from a 2009 paper with beaked whales, which I'll use later still as an example. And so there I will show you that we actually knew where the animals were in space and time. So we could pick up and evaluate for each one of the sounds the animal produced, whether it was detected or not on surrounding hydrophones, and therefore estimate this probability of detection, which is represented on that plot. I'll talk about it later when I integrate all this. But so that's another way of getting your probability of detection. Now, a third option to obtain the probability of detection is from acoustic propagation models. I guess the movie I chose here tells you how much I believe in them per se. So they're very nice, right? But what we often find is whenever you try them against measurements, something always went wrong. You need to tweak it. And so not having the reality to tweak it means that you're now dependent on a model, so things might go wrong. But if you're willing to believe it, as we did on that paper with beaked whales, you can actually, again, get your probability of detection, and off you go home free. Now, the third component required is that F there, which is a proportion of false positives. Now, there's not much to it. You just need to characterize your detector. If it's an automated detector, you need to know how many false positives you have. If it's a human detector, you need to somehow be able to evaluate the performance of the person. Here, I'm just taking that screenshot as an example. In that paper, we selected 30 random periods systematically spaced over the sampling periods, and a human went and manually decided whether those were beaked whale clicks or not beaked whale clicks in every given minute of the samples. So now you've characterized your detector, there's just one final thing missing. You're missing really the probability of, sorry, the Q rate. So that's what's the, you know, the food that accurate lives upon. So you need to know how many sounds are produced per unit time per animal. If you want to know more about the project, you can look on the webpage, look at our Twitter feed, and you'll see a bunch of little outputs, some outreach material, etc. But I mean, so Q counting, the idea, as I said, you want to convert the number of detected sounds into a number of animals. So of course, this Q rate multiplier is fundamental. And why is that? Imagine that you have a gigantic pool, okay, where you have some animals and you put some PAM recorders there and you pick up 100 sounds in an hour. Now, it's very different, the number of animals that will be in the pool, depending on the Q rate, right? The higher the Q rate, the fewer the animals. And so it's fundamental to know what's the Q rate production to be able to convert the number of detected sounds into a number of animals. Well, the issue is that pretty much everything else that you can think of will influence the Q rate. So the behavioral state of an animal, you know, dial patterns, the group composition, the age, environmental covariates, the sex, the ambient noise. And if you're really, really unlucky, even density could influence the Q rate. That would become totally circular because now I want to estimate density. That depends on the Q rate, but the Q rate depends on density. So you're kind of lost. In that case, there's nothing you can do besides trying to actually tag some animals or take some follows during the survey period to get the cue. Okay, but I mean, we don't know that much yet about the cue production of most of the animals that we are interested in, and in particular in cetaceans. So this is an example from a recent paper where my colleague Jamie Macaulay was looking at the implications of porpoise echolocation, and their dive behavior. So including also their click rates on passive acoustic monitoring, and he shows that clearly, depending on the behavior, very different behavioral states have very different cue productions. And so, for example, if you're comparing across sites, you might actually find that a site has more porpoises than other, just because on that site, the porpoises usually engage behaviors where they do more more sounds or less sounds or vice versa. So basically you need to know whether sound production is constant over space or not, and usually it might not be, to tell things apart. Now, something that it's worth pointing out, because here I guess there's a community of people which are really interested in the sounds, and the sounds have biological meaning to them. The cue rate that you need in a pan density exercise might not be biologically meaningful. No animal might actually produce that average number of sounds per unit time at any one time. What I mean by that is that you have to average across the silent periods. So it's not the sound production when the animals are making sound, which sometimes people report on papers. It's actually the long-term average, because that's what you're going to have to use to convert what you find in your sensors into an estimate of the density of animals. Now, just to highlight that most of what we do in Accurate comes from tiny devices compared to the size of the whales, that are put on the whales and record a bunch of things, including sound. Yeah, well, okay. I guess you should not do to the animals what you wouldn't do to yourself, so I always try the tags first. Now, just to give you an example of an output from the Accurate project, we had over 100 tags. There's like 160 tags, but here I'm only presented about 100 tags of sperm whales at 8 different sites across 13 different years. And there's been millions of echolocation clicks produced during those periods on those tags. These whales, they forage at depth, and so they produce most of their sounds while they are at depth. In that depth profile that you see, we've highlighted in red when the animal had produced the sounds. And so depth contains a lot of information about sound production. So actually these depth profiles might be available when they have no acoustics on them, because we could predict cue rate based on the depth profiles. And those, so that's one of the aspects that we've been exploring. We've also recently put out a note comparing different ways of analyzing these cue rates, and whether you should consider the units of analysis at the tag level. What we call the deep dive cycles. In the previous slide, you can see in that image that whale did these 8 deep dive cycles, 10 actually, 10 deep dive cycles, and people in the past have used these deep dive cycles as the unit of analysis. We've compared a bunch of approaches, and we've concluded that, in fact, differences are not major. These are the differences using slightly different methods. In green with the complete data set, and in blue with the reduced data set, where only the deep dive cycles shorter than an hour are present, which is equivalent to considering a different species with a slightly different diving behavior. And what we saw, I mean, and here am I highlighting, the paper that we did in 2009 really was doing pseudo replication, because as I'll tell you, we're only using 5 whales, that's all we have. And so instead of using the whale as the sampling unit, we use the deep dive as the sampling unit, and now we have 21 deep dives. But that's not really fair. Again, we only got away with it because it was proof of concept. I've come to realize that many of the papers in my career are like that. Like, I only got away because you know, it was kind of a bit new, but nowadays it would be rubbish anyway. Another of the methods we looked at was the one used by Warren et al. In 2017, which was using a regression model, a GE model, and basically we compared all these different things. Again, this GE might not be the best approach, and you can read the paper for details. But you know, at the end of the day, all these different methods actually provide numbers which, in the grand scheme of things, given that you have so many other unknowns, are not so bad altogether. And okay, you might think, what do I want? Do I want to wait, or do I not want to wait as a function of the tag length? Do tags with longer durations have more information or not on them? And it's actually not as clear cut as one might hope for. And again, if you want to look into this paper, there's a number of considerations at the end why you might do it one way or why you might do it the other. And I'm sort of illustrating different aspects of the analysis. For example, showing that if you do a weighted mean instead of a standard mean, naturally in the reduced data set, you kind of increase the estimated Q rate because you're now giving more emphasis to shorter deep dives, and usually those shorter deep dives actually have higher Q rates, and the opposite happens in the complete data set. Now, I'll skip that just to illustrate what I was saying. So if you look at these plots, on the top left, there's all the data, and on the x-axis, there's the tag duration, and on the y-axis, there's the Q rate. And what you see is that, sorry, I said that on the x-axis, this tag duration, but I meant deep dive cycle duration. So it's up to 6 hours. And what you see if you zoom in the first hour is that there's actually a pattern of increasing Q rate with time. But if you look at the rest of the longer deep dives, there's a decreasing pattern. So this correlation with duration makes it that it's not so easy to know what's the best thing to do. Finally, just to point out that the really interesting bit is how can we extrapolate these values to other times and places? And in fact, we're working on that using a fairly simple but Bayesian hierarchical model with space and time as random effects, where then we try to predict what would be the Q rate in a place that we have not observed. So in the right plot, on the right-hand plot, you see the Q rates using different methods for each one of the different site in year combinations for which we have enough data. That's more than 3 tags. So I'm very generous on what's enough data in this paper. But then you have those dashed lines which represent the mean and the confidence limits, 95% confidence limits of what would be an estimate of Q rate in a different time and place. Sorry, language mistake. These are not confidence intervals because it's a Bayesian analysis, so it's credible intervals, but for practical purposes, they convey the same kind of information. Now, just again as another example, we are working with the narwhals tagged in different places, some in East Greenland, some in Canada. And again, here we see that the animals click mostly while at depth. So we are exploring models to predict the number of clicks as a function of depth, and then trying to improve the estimation of the Q rates based on those models. Now, based on those models, you now have a relationship between depth and the predicted probability of being in a clicking stage, and also you're able to model the number of clicks within that clicking stage. And with those models, we then predict what would be the number of clicks at each one of these points in time. And using these kinds of models, you can then try to predict for new tags, which might only have the depth profiles. So these are just, as I said in the beginning, sprinkles from accurate, little different threads coming out of Accurate. That's just a table with the summary results for the 8 animals that we have. And we see that we have estimates of the Q rates with their precision measure. The details are not that fundamental here, but this would be the multiplier and the relevant precision measure that you would need if you wanted to estimate their abundance based on PAM recordings that you had from these kinds of areas. Now, another thread within Accurate, which is kind of interesting to me because I had not really thought about it in the beginning of the project, or until someone that was on the project mentioned it to me, is that we have tags on the animals, but actually for animals with low frequencies, baleen whales in particular, their calls are so low frequency, they travel so well that it's very difficult to find on the acoustic signal whether it was the animal that has the tag that is calling or a conspecific nearby. And that's an issue, because if I have a tag in an animal and I think that's only the sounds that that animal did, but that animal is with 5 other whales nearby, then I'm overestimating the Q rate by a factor of 5. And so we've been working on methods to identify on other channels of the tag, namely on the accelerometer channels, when can we see the vibrations coming through the body of the whale into the tag, and therefore allowing us to separate what is the tagged animal sounds and what are the sounds from conspecifics. Finally, another thread that we've been looking at is trying to use the PAM data. And so the PAM data would be something like the top right there. And the top right has the distribution of ICIs, interclick intervals, over a long period of time. And you see that there's a modal distribution. But what is interesting is if you manage to decompose that distribution into the different size classes, which is on the bottom plot, you actually see that they have different interclick intervals. So in some way, different size classes might have different Q rates. And with that knowledge, if you can undo that process, you might actually be able to estimate density using a site-specific Q rate. And that site-specific Q rate comes from data collected on the PAM data itself. So that makes it very easy to apply. Well, very easy after you had all the trouble to figure all these things out. Now, putting it all together, so all these components, I'm going to just showcase an example of when we did passive acoustic density estimation of cetaceans. So this was, I've mentioned it before, a paper from back in 2009, where we estimated abundance at a range, a US Navy range in the Bahamas for Blainville's beak whales. And so this is the Bahamas, and the star on the left plot is the range, and the blow up on the right plot is the location of 90 or 93 hydrophones that are recording sound in real time, 24/7. They're doing Navy tests and they record it 24/7. And every now and then, when there's nothing very secret going on, they allow us to see the data. And in those periods, we can try to do something with it, because on those phones, cetaceans are routinely detected. And so the Navy has a program just to deal with this kind of data and try to understand how the marine mammals might be affected by the sonars and experiences and procedures that they use. And that's kind of what funds LMR, that funds the Accurate project. Each one of those little wiggly things on the plot, it's not just a copy paste gone wrong. Those correspond to tracks at a very fine scale, where using the tags that we had on the back of some animals on the range, which besides the sound collect accelerometer and the magnetic field of the Earth in 3 axes, we were able to, using some slightly sophisticated statistical methods, reconstruct the 3D pattern of these whales. And because we have the acoustics on the tag too, we knew at each time point when a whale would produce a sound and where it was pointing. And all this information is actually quite fundamental, as you will see, because beaked whales, unlike most things terrestrial, they have their sound production very highly directional. It's almost like a flashlight in a dark room. So you only illuminate a little bit of the area. So it's important to know whether the whale is pointing at you or away from you to model the probability of detection. Okay, the data we had, we already saw the plot on the left. Those are the number of clicks detected on a bunch of periods. As you can see, there's 12 different sets. Some sets were not available to us because secret things were happening, whatever, using some sonars that they do not want us to know what's the frequency and range. But we could use the parts in between to count the number of clicks. Was about 3 million or so, if I recall correctly. And then we combine this information, so number of detected clicks we have. Someone got tasked with going to each one of the stars underneath the word set, okay? There's 30 stars there. Someone went to 10 minutes starting on that star and counting in each minute, in each one of the 80-odd hydrophones, whether the sounds there were of big whales or not. So evaluating the false positives. Then Q rates we got from the tags, as I said. So on the bottom right, you have the 5 tags we had. Remember I said we only have 5 tags. But when we think on the number of dies, we have 21, which strictly is pseudo-replication, as I said. Well, we did it. And then here is the result of the model I was telling you about. So I have a whale at each time. I know where it's pointing and I know the position of the hydrophones. So I can use trigonometry to find exactly what was the angle between the beam of the whale and the hydrophone. And this is the outcome. I do a logistic regression model, a generalized additive regression model. And what you see on the top left is the probability of detection as a function of distance. And what you see on the top right is the probability of detection as a function of changing the angle. So when you're pointing straight at the hydrophone, which is angle 0, 0, the likelihood of detecting that call is very high, and it decreases. This is kind of like a volcano or a mountain. It decreases as the whale points away from the hydrophone. And so we kind of use all that together in that one equation that you already know to get an estimate of 25 to 23 about animals. And that interval, those two estimates, were because when evaluating the false positives, it was really difficult to decide sometimes whether it was or not a beaked whale. So we played it safe and we said if it was all beaked whales, it's 25.3. If none were beaked whales, it's 22.5. So it sort of gives you a range. And that was it. Notice, I say there at the bottom, the overall variance of this estimate of density depends on those 4 different components by different amounts. If you will see, 66% is about the probability of detection, showing you that it's key to have that, but also 25% is about the Q rates. The other 2 components really carry a very small amount, in particular the false positive proportion, 1% of the total variance, because that's the easy one to get. You can just evaluate your detector as many times as you want to lower that number as much as you want. It's just a manpower. Okay, that was a roller coaster, quite fast, but it's time for a final story, and really just to say that interfaces of different fields are challenging, but they're highly rewarding. In general, you need to speak several languages. You do risk becoming, knowing a bit of many things, but nothing too much of any of them. And we need to think about the filters, because undoing the filters that we have on our data is fundamental, but can be hard. Passive acoustic monitoring is certainly a growing field. Q rates are fundamental to do Q counting, and we need more research on those because really the acoustic behavior of many species is still unknown. And there's lots of possible statistical developments within this realm, and I can talk to you about it if you are interested in those. But really, PAM, density estimation, is very promising, could be hard to implement, and it's not a panacea. Sometimes it will fail miserably. That's it. Thank you very much. Questions, welcome.
Brilliant. Thank you, Tiago. I think your knowledge of Hollywood movies might rival your knowledge of statistics. Really deep cuts in here. Does anybody have questions for Tiago about anything related to his presentation, film history?
I must admit, I spent 80% of the time putting movies in and 20% of the time doing the slides.
Well, hey,
But you
yeah,
challenged me, okay, Ben? That's that. When I saw that sentence, I go, "Oh my God, people are going to expect like great things," and so
that's part
maybe
of my
some movies.
job, I think.
Oh, it was very good.
Yeah. So, hey, everybody. You have questions or comments for Tiago? Love to take some now.
I have a question. I was just curious about the part of about who was calling with
Yeah.
mysticids with tagged to understand if the animal that was emitting was the one with the tag or a nearby individual. If you can give us a little bit of more detail about it,
Yeah.
because okay, thank you.
Okay. So, am I still sharing my slides?
Yes.
Yeah. Okay. So, what we have here in this image is on top is the sound channel on a tag. I think this was taken from a right wheel, and in the bottom was the accelerometer. And what we were showing was that unlike or illustrating, unlike what had been suggested before, where it seemed that this would be relatively easy, or at least there was hopes that this would be relatively easy, the kind of sampling frequencies that we have in some of the accelerometers are not really enough to pick up the vibrations of the sounds that the animal is producing. And so this method that we would otherwise have to tell who's calling might actually not work in many of the, if not most of the old tag records that we have. I think with newer tags sampling at higher frequencies and depending on the species, you might have a window of opportunity there. In terms of trying to understand who's calling at what time, there's also been quite interesting work done where there's Susan Parks and Franz Jensen. They've been working on groups of animals where they have multiple animals tagged at the same time. And so they can start to try to see whether the calls on the different animals have different sound levels on them, and then try to see whether, if you constantly see that there's a regular, say, sound production rate with lower amplitude on that animal but with higher on that one, then maybe that's that one's animal sounds. And so you can kind of mix and match across these. And maybe then, and this is just a maybe then, I'm just being speculative, maybe you can then use that information perhaps to train, say, a machine learning model to try to pick up signals that we're not seeing, but that there might be on the other channels or even on the sound channel. But this is all work in progress. And in fact, Susan and Franz would be able to tell you more about this.
Thank you very much. Very interesting talk. Thank you.
Thank you. Thank you very much.
Looks like we've got, let's see. I just lost we've got a few raised hands. So please, one of you unmute and we'd love to hear your question.
May I please ask a question?
Yes, thanks, Nanako.
Thank you so much for your amazing presentation. I have a question about the second slide from the last, I believe. You said that, oh yeah, thank you.
This one?
Oh, yes, that one, thank you. So I wasn't quite sure what you meant by you need to speak 2 or more languages. Could you please give more details on that?
Yeah, sorry. Languages in the sense of sort of scientific languages. So I guess to do something like, you know, a PAM density estimation exercise, you need to know a little bit about acoustics, maybe a lot about acoustics. You need to know about the statistical aspects. You might need to know about the engineering aspects of things, you know, hardware. You might need to know about the field work and, you know, maybe putting the tags on the animals or putting the sensors on the bottom of the sea. And so that's what I'm saying is that to work with these projects where there's data coming in and we want an estimate coming out, you need to be able to understand different languages, because people tend to use different languages in their niche. And then when you're trying to have these conversations in projects that really depend on on a large number of specialities, sometimes that conversation can take time. And so sometimes in big projects where people from very different areas have to work together, you really need to spend some time trying to understand the other and trying to understand what he's saying. And so I guess that was kind of out of the blue there on this take-home message slide, because I didn't really talk about it, but it's something that I felt being often at an interface between statistics and biology. Often biologists and statisticians have very different languages. I feel I can understand them both, but sometimes it's difficult to make the translation, make everyone happy at the same time. That's what I was pointing at with that bullet.
Thank you. I understood so much. Thank you.
Okay, let's go to Chris Clark and then Torbjorn.
Thank you very much, Tiago. And your point about multiple languages is pretty critical, because when those interfaces are not working very well, there's a lot of noise.
Yeah.
So I'm going to go back to you started out with a very urgent and emotional plea almost about climate change, or a realization about climate change. And that brings me back to asking you a question about why is density estimation important?
Okay. You mean within that context of climate change?
Well, right now, everything I see is within the context of climate change, but
right.
So, yeah.
Okay. Let me answer that question. So that's a rather more philosophical almost than about the science itself. I mean, I think it's important in many areas because we are putting all this pressure on the environment. And so some species, if not many or most, are struggling. Well, some benefit from it, but most of the natural species probably struggle. And therefore, to know what's happening, to try to manage them, we need density estimation. Now, if you ask me if sometimes when I'm late at night in bed thinking, should I be doing models on climate change rather than trying to count how many, caribou are in East Greenland? I often think that, to be honest. I go and think, should I be doing this? But then I also go, and it's a very personal answer, is, well, maybe then I should go into a hospital and save children which might die if I'm not there to help them, And so there's all these things which are pressing and urgent and important, and all these things which are long-term also urgent in a way. And I think density estimation is a small part in all that. I don't see it as the grand scheme of things. It happens to be what I do for a living in terms of my research is on density estimation. If I were to choose what's the big question, today I would be working on climate change, definitely.
So you, in your answer, though, first of all, you talk your personality as a humanist and as a compassionate believer in life, broadly speaking, is fully apparent, right? Those 2 o'clock or 3 o'clock in the morning moments of the hour of the wolf kind of thing, where what am I doing? And should I be doing something else? Those are something that I think everybody in this listening to this presentation needs to be aware of, because I think it happens to everybody, and yet we carry on. And sometimes in life, you may actually have a moment where you're saying, I need to be doing something slightly different. And you shouldn't be afraid of those moments in the middle of the night. But I will say that when we have benefited the science, if you will, of marine mammal counting and populations and dynamics has benefited greatly from your, hopefully not a detour into this whole realm of statistical applications, to understanding, well, when have we got it right and when do we not have it quite right, and how could we do it better? So that's, I mean, I think you probably know this, but maybe you don't hear it all the time, because you've been I don't know how, I can't remember really, really well how you managed to end up where you are. You just talked a little bit about it, but some of that I think it was driven by your personality, right? You're curious, you're generous, and you're boundlessly energetic about these things.
Well, Chris, you've made my day. Well, you might have made my week, my month, and my year, but thank you very much for those kind words. Very kind.
I mean it sincerely. Thank you for everything you've done.
Thank you. Thank you. Now you got me emotional. But anyway, let's moving on.
Thanks, Chris. All right, I'm going to need some time to reflect after this, but let's go to Torbjorn as well, who is also interested in density estimation, but in a very different type of environment.
Yeah, thank you. Thank you, Tiago. Very interesting talk. You mostly talked about moles, where you estimate that based on distance sampling and call rates and so on. So different class of models is where you try to locate the individuals and use more kind of spatial capture models. I'm thinking about work by Ben Stevenson and David Borchers and others. So I was wondering if you could say a bit about how those models compare and when you would sort of go down one line rather than the other. Yeah.
Absolutely. So, I mean, broadly speaking, there are kind of three ways you can go about estimating animal abundance, and all the ways involve this key concept of detectability, because that's the key aspect, is that some animals that you are in the units that you are sampling might not be seen, and you want to correct for that. So distance sampling is one way where and I'm doing it very general so that people that are in the audience can follow. So distance sampling is one way where you model the detectability as a function of distance. That's it. Now, in capture-recapture, that could be a possible way, okay? And standard capture-recapture, that could be a possible way if, for example, for some animals, we could uniquely identify them by their vocal behavior, right? So like speech recognition for humans, that could be a way to attempt to estimate them using the notions of capture-recapture. So the number of times you would pick up the same animal on different places and the number of times that you missed an animal on different places would tell you something about animals that you never saw. And that's another way, another realm of doing density estimation or abundance estimation. Finally, what you were just mentioning, which is spatially explicit capture-recapture or spatial capture-recapture. And there, the notion is that we have the different senses and the probability of detecting a sound. One key thing in there is that you have to have an array. So to do spatial capture-recapture, you typically have to have an array, because the information that you need is the detection of the same sound on different senses and your ability to actually synchronize such that you know this sound and that sound were the same and that sound too, but that one not, and it was missed there, kind of thing. And once you manage to do this, you can actually extract the information contained on that pattern of detections, non-detections, to tell you how detectability happens to be operating in this area. So I would say that if you are able to have a very good dense grid of sensors where you can do this assignment, spatially explicit capture might actually be ideal. It gives you exactly what you want. It can actually model density over space using that information. Usually I think about this notion of Q counting because in some way you need a little bit less information for that. You don't need the association across sensors. Of course, what I'm saying might not be true if I consider, say, a small array of hydrophones or microphones which are close together, time synced, which I can localize with. And then you can either do SECR or distance sampling. But in fact, in general, distance sampling and spatially explicit capture, you can actually formulate a framework of animal density estimation methods. And these two are at the end of each other, depending on the amount of information you have. In fact, is a paper with David Borges, Ben Stevenson, a few others that looks into that and does that sort of conceptual link between all of these. So I would say that in general, the first step, if you really wanted to do density estimation, is to sit down and think, okay, this is my animal, you know, my animal sounds like these with these kinds of propagations at these broad scales or very narrow. That will definitely drive the way you have to approach the question. And then given that, and then given also money, because of course I can tell you need to put 300 sensors in an area and tell me, well, I have money for 4, and now we have to adapt. I think it's really needed that we all sit together. So the person that knows the animals and the environment, the person that knows the sensors and how to use them, and someone that knows what the analysis methods and how they might be implemented given those constraints. And then from that conversation, a suitable or more appropriate method might arise. But it might not be an optimal method, you know, and you might conclude that passive acoustic density estimation is not the way you would go for your own species. So it really depends on the context. Not sure if that answered your question, Torgrim.
No, that was good. Thank you.
Tiago, do you have a few more minutes for our last 2 remaining questions?
Yeah, sure. Yeah, no, absolutely. Very happy to.
So Renata Susalima is saying oi, oi Tiago.
Well, we can do it in Portuguese, but the others will not like it.
So she was wondering if you think that there's any bias on which animals get tagged, maybe bolder ones, and would this influence your results on Q rate estimation?
Absolutely. And I must say that I'm not exactly sure how to answer. I don't know, but I suspect that in general, animals that will be tagged might be more in a state, you know, whatever, in a taggable state. Let's imagine that a female has a calf, and so she's very protective. And so whenever she hears something, she goes away. So in that case, maybe you would be more likely to tag, you know, young males, which are showy and quite, you know, adventurous. And if you have differences in sound production across these two, you know, classes, you could definitely get into trouble. This goes for tagging, goes for anything else. You know, quite recently with a master's student here in Portugal, she was doing just as a proof of concept, trying to use it PAM density estimation for some birds. And we kind of realized that, you know, she was doing focal follows to get the Q rates, but you focal follow the ones that you found acoustically first in a way. So in a way, you've already queuing on those that might be on a higher sound production state. So I think critically thinking about what are the animals that you're tagging are fundamental. And I'm going to torpedo myself yet again to say, like, I mean, if you have 6 tags, let's say that's 6 tags, even if there's no actual bias, and even if all the animals were singing at a common rate from a pooled process, there's natural variability, right? You could have 4 weirdos and 2 normal ones, and you get an overestimate of the population Q rate, even though there's no actual factor. It's just individual variability. So I think we need to be careful. It's as with everything. When you're sampling animals and the sampling is from some sort of convenience process, because you managed to tag them, because you managed to follow them, you have to wonder whether you might be biasing. That's my answer. So yes, be careful, Renata. Há que ter cuidado, minha amiga, não é fácil.
I had a question regarding the filters and the future of density estimation. Like, if we assume, that this field continues to grow with regards to better software, and so, reliable detection becomes increasingly something we can bet on. And let's say that problem, dissolves away to some limit. So we have reliable detection, and then we also have much cheaper hardware, and so we're able to deploy more units out there. Like, what becomes of the filter, or like the remaining,
the constraint? What's left to? Yeah. Well, and to be honest, I think this behavioral aspect, where we really need more work on that, understanding the sound production, because we're literally relying on something that the animals produce to count them. Therefore, if we don't understand that process, we might be really wrong, right? So the other option, like I was saying before, if I was doing animal voice recognition, and if that's possible, it has been shown promising for a couple of taxa in particular situations. Then you're home free. You just really need to find new voices, and that's it. So in that context, with good sound processing and good sensors, I mean, it will be easy, he said as famous last words. But if you don't have that luxury, and you really need to use the number of sounds and convert those into density, the key constraint, the key bottleneck, I suspect, will still be this Q production rate, because we will not know whether what we have is really what we think we have, unless we understand the acoustic ecology, of the species of interest. And let's face it, we know very well the acoustic ecology of a few species which have been models for a number of things. For some of these animals at sea, we don't even know which are the sounds they make. They're still describing, oh, that sound is from that whale. So that's how far you are from having something that's actually routine. Okay.
Yeah.
Anyway, I forgot to say, and I leave that there. There's my email there. I'm very happy to answer questions that people might have about, estimating density from passive acoustics. I'll try to answer. I'm actually under a horrible semester with 15 hours in class per week. That's why I said I have the students in class, but I'll try to answer everyone that sends me an email.
Brilliant. Well, Tiago, thanks so much for joining us, and everybody for tuning in. We'll be meeting next week. I believe it's on the 6th, actually, so not on a Tuesday, December 6th. And here we'll be meeting with some, I think they're anthromusicologists, researchers, ecologists, anthromusicologists, talking about multiple languages, but also with these traditional fishermen from Dakar, Senegal, who use the soundscapes of marine environments as their spearfishing. So this will be a different kind of BioacousTalks, but one that I hope will be quite fascinating, a different dimension. And then on the 12th, we'll then be joined by one of my top 3 favorite field recordists, who's been really prolific these last, I'd say close to 10 years, George Vlad, and that will close us out. So Tiago, thanks so much for today's talk. It will be posted soon on YouTube, and we'll see you guys on the 6th.
Thank you very much, Ben. It was a pleasure being here. Take care.
Bye-bye.